The lightest metal in the world, lithium, has become a strategically important raw material for Earth's economy due to the spread of lithium-ion batteries. And as bad luck would have it, this very element, which we need so much, turns out to be extremely rare on Earth. Known lithium reserves amount to only 26 million tons, which is twice less than the known reserves of gold, platinum, or the uranium-235 isotope suitable for use as nuclear fuel. And moreover, lithium appears to be a great rarity on the scale of the entire universe, which is rather strange. For most chemical elements, there is a fairly simple pattern. The lighter the element, the more of it exists in the universe. This is not a strict law. There are both peaks and dips on the element abundance curve. However, the general trend is exactly this, and lithium, along with its neighbors in the periodic table, beryllium and boron, sharply deviates from this trend. So, just by looking at the element abundance curve in the universe, it becomes clear that something is very wrong with these elements. The answer to the question of what exactly is wrong with lithium has several levels. And by going through all of them, we will not only get this answer, but also get acquainted with the laws governing the formation and existence of atomic nuclei. In general, our journey into the world of nuclear physics today promises to be interesting, though not too simple, so make yourselves comfortable, and let's go. To begin with, let's ask ourselves where the various chemical elements that surround us and make up our own bodies actually came from. About 380,000 years after the Big Bang, when the so-called era of matter began and continues to this day, the universe was filled with atoms of the simplest chemical elements. Hydrogen, whose nucleus consists of a single proton and sometimes one or two neutrons, as well as helium with two protons and one or two neutrons. All the diversity of chemical elements we observe in the universe today formed later, as a result of thermonuclear fusion reactions occurring in the depths of stars. Synthesis is the process of forming complex nuclei from simpler ones containing fewer nucleons, meaning protons and neutrons. Nuclear fusion becomes possible due to a phenomenon known as the mass defect, where the mass of a nucleus is always less than the total mass of the nucleons composing it. This phenomenon is explained quite simply. The mass of an atomic nucleus equals its rest energy, meaning the energy in a state where the nucleus's momentum is zero, divided by the square of the speed of light. The rest energy of the nucleus, in turn, consists of the total rest energy of the nucleons, meaning the sum of their masses multiplied by the square of the speed of light, plus the mechanical energy of the nucleons, meaning the sum of each one's kinetic and potential energy. The interaction forces in the nucleus generally have an attractive nature, meaning the potential energy will be negative. Moreover, since the nucleus is a stable object, we can be sure that the negative potential energy of the nucleons in absolute value is greater than their kinetic energy. Otherwise, these nucleons would simply fly apart. That is, the total mechanical energy of the nucleons in the nucleus will also be negative, and the overall rest energy of the nucleus, which determines its mass, will be less than the total rest energy of the nucleons, leading to the emergence of the mass defect. This very quantity, the total negative mechanical energy of the nucleons in the nucleus, taken in absolute value, is called the nuclear binding energy in nuclear physics. And the mass defect turns out to be equal to this energy divided by the square of the speed of light. In nuclear physics, another quantity is often used, the specific binding energy per nucleon, meaning the nucleus's binding energy divided by the number of its nucleons. This value is convenient because it shows how well assembled a given nucleus is. The greater the binding energy per nucleon, the more strongly the nucleons are bound in the nucleus, and the more the nucleus's mass is reduced compared to the mass of individual nucleons. Roughly speaking, two nuclei with a lower binding energy per nucleon will find it energetically favorable to merge, forming a nucleus with a higher binding energy per nucleon, since the total energy and thus the mass of such a nucleus will be lower than the total energy and mass of the components. And it turns out that for elements at the beginning of the periodic table, the binding energy per nucleon increases rather quickly as the atomic number grows. Understanding why this happens is not difficult. In the nucleus of deuterium, which consists of one proton and one neutron, each nucleon interacts with only one other nucleon. Whereas in the nucleus of, say, helium-4, each nucleon will already be attracted to 3 other nucleons, meaning the binding energy per nucleon will be higher. If so, the state in which 4 nucleons combine into the helium-4 nucleus will be more energetically favorable than the state where they are combined into 2 deuterium atoms. The more nucleons in the nucleus, the more nucleons each one will interact with, and the greater the specific binding energy will be. And this is precisely why forming more complex atoms from lighter ones is a more energetically favorable process, meaning this process occurs naturally, provided that the necessary conditions for such reactions exist in the form of high temperature and pressure. And such conditions are indeed found in the cores of stars. Physicists call this process stellar nucleosynthesis. However, if we look at how the specific binding energy per nucleon changes as the atomic number of an element increases in the periodic table, we will see that the rate of this growth gradually slows down. Then the binding energy reaches a maximum and begins to slowly decrease. This maximum occurs in the region of the periodic table where iron and nickel are located. And therefore this region in nuclear physics is also called the iron peak. And since we said above that fusion occurs when the specific binding energy per nucleon of the reaction product is greater than that of its components, we can conclude that elements heavier than iron should not form in nuclear fusion. Indeed, since the formation of such nuclei from lighter ones would lead to a decrease in the specific binding energy and an increase in the total rest energy of the nucleus, meaning its mass, for this process to occur, additional energy must be poured into the reaction, and an external energy source is needed to initiate and sustain such reactions. In the universe, such a source is the colossal energy released during supernova explosions. Yes, every atom of chemical elements heavier than iron, such as silver, gold, platinum, mercury, lead, or, for example, xenon, not to mention uranium, was once formed in the monstrous melting furnace of a supernova explosion. But here's the question: why does the binding energy at a certain stage stop increasing and start to decrease? After all, we just said that the more massive the nucleus, the more nucleons each nucleon interacts with, meaning that as the number of these nucleons grows, the binding energy should increase indefinitely. That is true, but above we considered only the interaction of nucleons within the framework of the so-called strong nuclear interaction. However, this is not the only interaction in nature. For example, electromagnetic interaction, which causes positively charged protons in the nucleus to repel each other, has not been cancelled. Yes, electromagnetic interaction is much weaker than the strong nuclear force. However, there is something in which electromagnetism surpasses nuclear forces, and that is the distance over which it acts. The strong nuclear interaction is practically absent if objects are farther than 10 to the minus 15 meters or 1 femtometer from each other. Electromagnetic interaction, however, does not have such a strict distance limit. Its energy decreases with distance, but never completely drops to zero. It is important to understand that the radius of nucleons is approximately 1 femtometer, whereas the radii of nuclei can reach tens of femtometers. In other words, in reality, each nucleon interacts not with all the nucleons in the nucleus, but only with its closest neighbors. The strong nuclear force simply does not reach nucleons in more distant parts of the nucleus. But electric repulsion between protons does reach, and therefore, the more protons in a massive nucleus, meaning the higher the element's number in the periodic table, the more strongly each of these protons is electrically repelled from the nucleus, whereas the strong nuclear attraction to the nearest neighbors remains almost unchanged. That is, each successive proton will be attracted to the nucleus more and more weakly, and at a certain point, the specific binding energy should start to decrease as the atomic number increases. And this is exactly what we observe in practice. We have taken yet another step closer to understanding the processes governing the formation of atomic nuclei, but we are still not close enough. For example, we still cannot answer the very question with which we began our video. Why are lithium, and its neighbors in the periodic table so rare? More precisely, there is something we can say right now. If we measure the mass of a lithium atom, calculate its mass defect and the specific binding energy per nucleon, we will be surprised to find that this energy turns out to be very, very small, much lower than, for example, that of a helium nucleus. The specific binding energy of nucleons in the atoms of lithium's neighbors, beryllium and boron, also turns out to be unexpectedly low, though still not quite as small. From this, we already understand that lithium cannot form in stars through nuclear fusion, the process by which other light elements formed, and it is perfectly logical that there is so little of it. But why does lithium have such a low specific binding energy? None of the nuclear models we have considered explain this in any way. The lithium nucleus is small. All nucleons in it should interact with all others. There are only 3 protons in it. By all reasoning, lithium's specific binding energy should be somewhere between the binding energies of helium and carbon, and this dip, which we might call the lithium valley by analogy with the iron peak, should not exist. By the way, there are other well-known phenomena that are not explained by our model. For example, according to it, in principle, it should be possible to create arbitrarily heavy isotopes of chemical elements, meaning nuclei containing an unlimited number of neutrons. Indeed, neutrons have no electric charge and do not experience electrostatic repulsion, meaning that no matter how many neutrons we stuff into a nucleus, it should remain stable. However, this is absolutely not the case. In reality, if we try to attach an extra neutron even to light helium-4, it will not be easy. First, the neutron will refuse to stick on its own, and we will have to spend about 750 kilovolts of energy to attach it. But the main thing is that the result of this attachment, the helium-5 isotope, based on the total number of nucleons in the nucleus, will be extremely unstable and will decay in just 10 to the minus 24 seconds by ejecting that very neutron. In short, there is definitely some other, as yet unaccounted for factor influencing nuclear physics. It turns out that this has to do with a property of quantum mechanical objects known as spin, and a related phenomenon known as the Pauli exclusion principle. We had a separate video explaining what spin is, where we elaborated that spin is the intrinsic angular momentum of quantum particles. For those who are entirely unfamiliar with the concept of spin, I suggest watching that video first before we continue. But for now, the detailed essence of this phenomenon is not that important. Essentially, we only need to know that nucleons, i.e. protons and neutrons, have this characteristic, and that the spin of a specific nucleon can take 2 possible values, +1/2 and -1/2, or, as physicists and chemists say, spin up and spin down. Now, the Pauli exclusion principle states that particles with half-integer spin, including spin 1/2, which are also called fermions, cannot occupy the same energy state in the same system unless their spins are oriented in opposite directions. With this knowledge in mind, let us return to constructing atomic nuclei from simple to more complex ones. The simplest nucleus of the lightest hydrogen isotope, known as protium, is not interesting to consider. There is nothing to discuss, as it consists of just 1 proton. The simplest composite nucleus is deuterium, made of 1 proton and 1 neutron. A proton and a neutron are different particles, so from the perspective of the Pauli principle, it does not matter how their spins are oriented. They can be arranged in any way. However, in practice, it turns out that these spins will always be aligned in the same direction, say, upward. Why this happens, we will explain a little later. By the way, let's ask ourselves, do atomic nuclei consisting of 2 protons or 2 neutrons exist? It turns out that they do, but they are extremely unstable and exist for only an incredibly short time. Why? Precisely because, due to the Pauli exclusion principle, the spins of nucleons in such nuclei must necessarily be oriented in opposite directions, and also due to another phenomenon related to the presence of spin, the so-called exchange interaction. We also have a separate video about it. where we explained that the nature of a particular interaction between two quantum particles depends on their spins. For example, if the spins of electrons are aligned in the same direction, they repel each other more strongly than when their spins are in opposite directions. In other words, their interaction is weaker when the spins are opposite compared to when they are the same. The same applies to the strong interaction. Nucleons with the same spin direction interact more strongly than nucleons with opposite spin directions. However, in the case of the strong nuclear interaction, this interaction is attractive rather than repulsive, and this nuclear attraction between two nucleons with opposite spins turns out to be noticeably weaker compared to the attraction of nucleons with aligned spins. Moreover, the weakening is quite significant, to the extent that in the case of two protons, it becomes even weaker than the force of electric repulsion, making such a proton system unstable. For two neutrons, the situation is essentially the same, except there is no electric repulsion between them. So in principle, a system of two neutrons can form, but its binding energy is so small that it can break apart from practically any disturbance, which it successfully does. So out of these three two-nucleon nucleus variants, the only stable system is one proton and one neutron, the deuteron, meaning the nucleus of a deuterium atom. Increasing the number of particles in the system to 3 is already quite simple. We can insert either a proton whose spin is opposite to the first proton, or a neutron, which will increase the binding energy per nucleon and thus be energetically favorable, making both helium-3 and hydrogen-3, or tritium, relatively stable. I say relatively because the tritium nucleus has a way to become even lighter by converting a neutron into a proton, which weighs about 0.1% less than a neutron. Yes, in such a nucleus, the presence of electric repulsion between protons reduces the binding energy and increases the mass. But overall, the configuration with 2 protons and 1 neutron wins out. There is no problem in adding a second neutron to helium-3, forming helium-4. However, if we try to add a 5th nucleon, we will already encounter certain difficulties. Indeed, the Pauli principle will forbid its attachment, since it will inevitably have the same spin as one of the particles already present in the nucleus. However, there is a way to bypass the prohibition. I remind you that the Pauli principle forbids the coexistence of particles in the same state, meaning, roughly speaking, with the same energy, momentum, and other characteristics. However, it does not apply when the particles have different energies. And so, in order to stick another nucleon to the helium-4 nucleus, this nucleon must have a higher energy, more precisely, a higher mechanical energy. The fact is that quantum particles in a bound system cannot have arbitrary values of kinetic and potential energy, but only strictly defined ones. We are well familiar with this phenomenon from the behavior of electrons in a bound system such as an atom, where electrons can only occupy specific energy levels. In the nucleus, essentially the same thing happens. Nucleons in the nucleus can only have discrete, quantized values of mechanical energy, meaning they occupy different energy levels. And to attach a 5th nucleon to the nucleus, this nucleon must be placed on a higher energy level, which requires adding extra mechanical energy. We remember that the total mechanical energy of nucleons in the nucleus is negative, and the absolute value of this energy is what we call the binding energy. By adding some positive energy to the negative mechanical binding energy of the nucleus, we reduce the absolute value of the negative mechanical energy. This means that the binding energy and the specific binding energy per nucleon also decrease, and the nucleus mass increases compared to what it would be without considering spin effects and the necessity of placing the next nucleon at a higher energy level. Moreover, it turns out that to place a nucleon on the first excited energy level, it needs to gain quite a large amount of energy, around 20 megaelectron volts. Because of this, the nucleus with 3 protons and 2 neutrons, meaning the lithium-5 isotope, gains a significant increase in its energy and mass, greater than the gain in binding energy that it receives due to the presence of a new fifth nucleon in the nucleus. This is precisely why the specific binding energy and mass defect for lithium turn out to be so small, which we observe as the very lithium gap. Furthermore, even if we artificially create such a nucleus by spending energy to attach another proton or neutron to the helium-4 nucleus, the resulting nucleus will be unstable and, in an incredibly short time, will eject the attached particle, since its energy, and therefore its mass, will be greater than the total mass of the helium-4 nucleus and a proton or neutron, making it energetically more favorable for these particles to exist separately. To stabilize the nucleus, another particle must be added. For example, instead of attaching just a proton, we should attach a proton and a neutron. Yes, the sixth nucleon will also have to be placed at a higher energy level, but the increase in binding energy that such a six-nucleon nucleus receives will be greater because each nucleon will now attract 5 instead of 4 other nucleons. And although such a nucleus, specifically the lithium-6 nucleus, will still have a very low binding energy per nucleon and an abnormally high mass, it will no longer be able to decay, since the ejection of either the proton or the neutron would push the system into an even less energetically favorable state. It is easy to see that adding another neutron to the helium-6 nucleus will also be energetically favorable, leading to the formation of the lithium-7 isotope. This neutron will also be placed at a higher energy level, but it will already be attracted to 6 nucleons in the nucleus, and each of these 6 nucleons will be attracted to it, resulting in the binding energy per nucleon increasing from 5.3 to 5.6 mega-electron volts. In other words, after the sharp drop in the specific binding energy for lithium, the first element whose nucleons are forced to start filling a new energy level, this binding energy gradually increases as the atomic number and the number of nucleons in the nucleus grow. And we can expect it to reach a maximum when the excited nuclear energy level is completely filled. More precisely, not just the level, but the levels, 2 different ones for protons and neutrons. And once one, or even more so, both levels are filled, we obtain a nucleus with a relatively high binding energy compared to its neighbors, one that forms relatively easily as a result of various nuclear transformations, and is relatively difficult to decay, meaning such nuclei should be relatively abundant in the universe. Here it is worth noting that the first excited energy level of an atomic nucleus can accommodate not just 2, but a total of 6 nucleons. Why this is so is a separate and interesting question, and we will definitely answer it in one of our future videos. Right now, what matters is this. For the first excited energy level to be filled, or more precisely, for both first excited levels for neutrons and protons, there must be 6 of them in each. And considering the 2 protons and 2 neutrons at the ground level, that makes 8. And indeed, a nucleus with 8 protons and 8 neutrons is the stable oxygen-16 with a very high specific binding energy of nearly 8 mega-electron volts, which exceeds the binding energy of isotopes of both nitrogen and fluorine, which follows it. As expected, oxygen turns out to be a fairly abundant chemical element in the universe, with 99.8% of all oxygen atoms being oxygen-16. Nuclei in which one of the nuclear orbitals is completely filled are called magic in nuclear physics, and nuclei where both orbitals are filled are called doubly magic. The name isn't great, but by this stage in physics, scientists had grown fundamentally tired of coming up with sophisticated terms for the phenomena they discovered and started naming them quite randomly. By the way, this whole story about magic nuclei is the reason for physicists' interest in the yet-to-be synthesized element with the working name unbihexium, with atomic number 126, meaning 126 protons in the nucleus. More precisely, they are most interested in the isotope unbihexium-310, which has 126 protons and 184 neutrons. It is expected to have both outer nucleon shells completely filled, which should give it a relatively long lifetime, minutes or even hours. whereas artificially synthesized elements usually exist only for fractions of a second before undergoing some form of decay. If unbihexium's lifetime does indeed turn out to be this long, it will serve as excellent confirmation of the correctness of our understanding of nuclear physics. Moreover, unbihexium could be used as a material for synthesizing even more massive nuclei, for example, to finally determine whether the periodic table has an end. Additionally, this story about nuclear orbitals helps explain why nuclei with a very large number of neutrons will be unstable. To bypass the Pauli exclusion principle, these neutrons would have to be placed at extremely high energy levels, requiring too much energy, making such nuclei once again energetically inefficient. But let's return to lithium. If helium-4, with both of its main energy levels filled by 2 protons and 2 neutrons, is doubly magic and super energy efficient, then lithium, and in particular lithium-6 with 3 protons and 3 neutrons, is anti-magic. The first element where we are forced to open an excited energy level in order to gather the required nucleons, which leads to a sharp drop in the specific binding energy per nucleon. This is precisely why the formation of lithium nuclei from lighter elements like helium or hydrogen is energetically unfavorable and thus impossible through thermonuclear fusion. Stellar nucleosynthesis essentially skips over the elements of the lithium gap. In the reaction of so-called helium burning, for example, 3 helium nuclei merge to form a carbon nucleus, or 4 helium nuclei form an oxygen nucleus. So how did lithium, which is now present on Earth, form? Most likely, it was the result of a completely different process, in which parts of more complex atomic nuclei were split off under the influence of high-energy radiation. This process is a far less efficient mechanism for producing atomic nuclei than stellar nucleosynthesis, which is precisely why lithium is so rare in the universe. However, some time ago, astronomers, to their great surprise, discovered stars in the universe that contain quite a lot of lithium, so much that it appears as if it were somehow being produced in nuclear reactions inside the star, which, as we saw above, should be impossible. At present, there is no explanation for this phenomenon, and these lithium-rich stars remain one of the yet unsolved mysteries of our universe. And we will certainly talk more than once about these and other mysteries and enigmas in our future videos. And if you enjoyed this video, or if you simply like what is happening on our channel, I ask you to support its work by becoming a sponsor, here on YouTube or on Patreon and Boosty. A link to the latter should now appear on your screens, and all necessary links will also be in the video description. A huge thank you to everyone who supports the development of the project. All the best, dear friends. And see you again in our next videos.